GCSE and A-level maths are different to the exams that actually get you into university, such as the British Maths Olympiad, the MAT, STEP, TMUA, because A-level and GCSE problems are structured in a way that they're testing whether or not you have learned what's on the syllabus, whereas these exams, these specialised exams, focus on your ability to solve problems that you might not have seen before, problems that are difficult, problems that require outside-the-box thinking. But there are strategies, there are techniques that you must apply, that you need to apply, that everyone that solves these problems applies. And these apply to every single type of problem that you might need to solve. So what I have for you are 4 tips. 4 tips that you can apply whenever you want. You can start applying these right now. You can attempt this problem on your own. You can attempt different problems at this level. This problem is from the British Maths Olympiad, round 2, 2025, and it's the first question. So this is a problem targeted towards the most able students in the 17, 18, 16 age range. And it's perfectly doable. It's perfectly doable with a GCSE understanding of algebra. And oftentimes that's how these questions are constructed. So let's start with tips. Tip number 1, read the question and use it. So let's read the question. Let's take as much information from this problem as we can so that we can use it. And just fundamentally, you obviously need to understand the question, and there's little bits and pieces that sometimes slip through the cracks. So if n is a positive integer, so n equals 1, 2, 3, so on, then 1 over n, which is 1 over 1, 1 over 2, 1 over 3, and so on, can be written as the sum of different triangular numbers. So what does that mean? Well, they tell us what a triangular number is, in that we have k plus 1, divided by 2, and this is the kth triangular number. Well, let's invert this. Let's take the reciprocal of that. So we have 1 over tk. That's going to be equal to 2k plus 1. Okay, and what they're saying is a finite sum of these reciprocals should give us 1 over n. Some finite sum. We don't know which triangular numbers to sum. It could be the 5th triangular number, or 1 over each, but the 5th plus the 10th plus the 15th plus the 11th plus the 115th. We should be able to make any 1 over n for any positive integer n that we choose. Our second step is to try whatever you can, which sounds obvious, but it's unbelievably important, because the only way for us to find patterns that we recognize is to do what we know how to do, because that's how we found them in the past. So let's try and see what we can do. Well, 1 over n here is clearly the easier part to deal with. So let's try and deal with this guy, this 2 over k plus 1. Okay, if we have a fraction where we have 2 terms in the denominator, our instincts might be, let's try and split that up. Let's try and turn that into 2 fractions. And that might not be something that you know how to do. But again, this is an instance where we both try whatever we can and we generalize. So let's say that there is some split of 2 fractions here that works. We know what the denominator should be. It should be k and k plus 1. And then we just don't know what the numerators are. So let's generalize. Let's just say they're two variables, and we are to work out what they are. Well, here, notice that if we just cross multiply, we get the same denominator as 2 over k times k plus 1, and we should be able to impose some conditions on a and b so that we can figure out what they are. Well, looking at this, if these 2 fractions are equivalent and the denominators are the same, then the numerators must be the same. You know, if I have some amount of a third of a pizza and someone else has some amount of a third of a pizza, and we have the same amount of pizza, then we have the same number of thirds of pizzas. Simple as that. So we know that 2 is equal to, and just factorizing here, a plus b plus a. Okay. Well then, we have this k here. And remember that k depends on which triangular number we're looking at. So let's say a plus b could be anything. A could be anything. And if k is 1,000, then, we can probably find values for a and b, but we want a and b to be the same regardless of what k we're using, which is why we're dealing with a specialized, specific arbitrary k here. So in theory, if this a and this b cancel each other out in that a plus b is equal to 0, and a was just simply equal to 2, well then we can look at b and say that it's just minus a, which is minus 2. So we found a and b, and we can go back and say that 2 over k plus 1 is equal to 2 over k minus 2 over k plus 1. This is nice. This is definitely simplified, and we have the same numerator, but we have distinct denominators, both related to k. So what can we do? What can we do with these? Well, again, let's try and simplify. Well, first, let's try whatever we can, and then let's simplify. Let's say we're stuck here. Let's say we don't know what to do. Let us just look at the next triangular number. So if this is 1 over tk, what does 1 over tk plus 1 look like? Well, it will be the same, but k is k plus 1. So every single thing to do with k, we can just increase it by 1. So we would have 2 k plus 1 minus 2 over k plus 2. We'll write the next one down, and we'll see if there's anything that we can do from that. Well, you might notice here that if I were to add these two together, as in these two, that we would get a cancellation. Likewise, if we look at the next one, well, we already had this cancellation, then these two also cancel. So whenever we sum consecutive triangular numbers, we get cancellations in all of the middle terms, and we're left with the first term of the first one and the subtractive term from the last one. So why don't we sum all the way from sum k to, again, we're going to generalize, to sum k plus a, and we don't know what a is. So summing to 1 over t k plus a, we'd see that, well, all of the middle terms would cancel, and we'd be left with 2 over k minus, and notice here that we just increment by 1, minus 2 over k plus a plus 1. So this finite sum of consecutive triangular numbers simplifies to essentially just two terms. Well, k is a positive number. A is a positive number because we went up from k by some a. So when we add 1 to that, this k plus a plus 1 is essentially still just a positive number, which is bigger than k. So why don't we generalize? So we start at some triangular number and we go up to some other triangular number. Well, let's say 2 over a minus 2 over b, and this should equal to 1 over n, and we're looking for the numbers a and b. Again, we've generalized here. Why don't we simplify? We can simplify this. So instead of having one equation and two unknowns, which we can't solve, why don't we make it so that we only have one unknown? Well, 2 over n is obviously bigger than 1 over n. So when we subtract 2 over b, which is less than 2 over a, because b is bigger than a, we should hopefully be able to end back up at 1 over n. Now this is extremely simple to solve. So if we just move that 2 over n to the other side, we end up with 1 over n minus 2 over n, which is of course minus 1 over n. And here we have 2 in the numerator, so why don't we just multiply the top and bottom by 2, which is the same as multiplying by 1, so that we end up with minus 2 divided by 2n. What does that tell us? Well, again, comparing denominators, we see that b equals 2n when a equals n. And let's just verify that. So if we have 2 over n and we take away 2 over 2n, those 2's cancel in that subtractive term. So we're left with 1 over n, which is the result that we want. So what does that mean? Well, we want 1 over tk plus plus 1 over tk plus a to be equal to, which is equal to 2 over k plus 2 over k plus a plus 1, rather minus, important, is equal to 2 over n minus 2 over 2n. Well, clearly, k equals n, in which case k plus a plus 1 is equal to n plus a plus 1 is equal to 2n. Now, just saying that a is equal to n minus 1 allows us to see that, well, the number that we sum to, which is k plus a, must be equal to, and k is n, so n plus n minus 1, which is 2n minus 1. So the sum from the nth triangular number all the way up to the 2n plus 1th, 2n minus 1th triangular number gives us 1 over n. And we've solved the problem using nothing beyond GCSE maths. So if you want to see how to solve more of these problems using tips that you can apply to whatever it is that you're doing, make sure you subscribe.